most of you have probably used a microwave at one point in your life. It's a very convenient way to heat up food. Now, as you may know, the microwave works by using electromagnetic energy in the form of microwaves. And those microwaves go into our food, and they hit water molecules. And the water molecules absorb the microwaves, and they vibrate, and that produces heat, which will then heat up your food. Now, this is an important application of molecule movement. Molecules are actually continually moving at all times. So if we look at molecules like alkanes, these are going to be free to rotate and move around as well. So here's my ethane alkane molecule. I'm showing it here with my dashes and wedges. Remember that the wedges represent hydrogens coming out towards me, while the dashes are hydrogens going back towards you guys. I can draw it here on my board in this nice flat structure, but it's actually going to be constantly rotating and rearranging itself, similar to my water molecules when I'm using the microwave. Now, of course, they won't be doing it to the same extent as my water molecules, but they still are free to move around and rearrange themselves. So this is all based on the fact that my bond here, if you remember, is a sigma bond, where we have the two heads of our sp3 orbitals overlapping, and so that bond can actually freely turn without breaking, right? I'm just rotating those two heads, and there's no real change in my bond there. Now, although my molecule can freely rotate, that doesn't mean that every orientation of my molecule is the same, and there's no difference. So we need to look at these different conformations, which are just different ways of arranging our molecule, and we need to consider how those conformations affect the stability and the properties of our molecule. Okay, so we're going to take a closer look at these conformations using my ethane molecular model shown here. I have my two carbon atoms here in the middle, one marked in red, one in black, and then I have my 6 attached hydrogens with these yellow covalent bonds. So my main conformational change can occur through rotation of my bond here, right? So my bond can freely rotate, and this can move around. I refer to this rotation as a change in my torsion angle or dihedral angle, right? So if I look head on, I have these both lined up, and then if I rotate this, so this would be an angle of 0, and I'm rotating it, the amount that I've rotated is my current dihedral angle. So I can rotate it to any position I want. And we can show those using my model. We can also draw those using a couple of different representation systems. Both of these are going to try to represent this 3D state in my 2D marker board. So the first method is a sawhorse method. And basically what we're going to do is we're going to kind of hold this at an angle so we can see both atoms. And we're going to try to draw it out like that. So with my sawhorse, I have my carbon in front, and then I show the bond going back to my carbon in the back with the hydrogens coming out there. So my sawhorse would look something like this. Of course, my representation over here is my standard wedge dash representation. Now both of these, they're trying to represent that three-dimensional shape on my two-dimensional structure. The next approach that we'll use is called a Newman projection. Now if we want to see the angles, the dihedral angles as I'm rotating my bond, the easiest way to see that is generally looking straight down between the bonds of my two carbons. Right? So as I look at this head on, you can clearly see the hydrogens on my back carbon rotating as I rotate the bond. So what I'm going to do for the Newman projection is try to draw this on the marker board with my two carbons overlapped, so we can just look at the relative angles of my hydrogen. So I'm going to represent my overlapping carbons in my Newman projection with a large circle. So this is representing those two carbons that are overlapping, and I'm looking down that bond between my two carbons. And I have my hydrogens from the carbon in front. So these three hydrogens are all connected to my carbon in the front. My carbon in the back is kind of hiding behind this circle that's representing those overlapping carbons. So I'm going to show my hydrogens kind of peeking out from behind this circle since they're bonded to that back carbon. So now we have three different ways of representing our conformational states of our alkanes. And now we can take a closer look at how these conformations might be different between as we rotate our carbon-carbon bond. So we're going to take a closer look at our conformational states using this graph here. So we're going to look at the energy of each of our states here on the y-axis, and we'll look at the torsion angle as we rotate our bond here on the x-axis. So we're going to look at our ethane structure here. Again, I'm looking at it in essentially my Newman projection where we're looking straight down the bond between our two carbons. This is at angle 0. So we have our 0 angle right here, 0 degrees. And if we look at the structure here, my little Newman projection, now the key thing to remember is that each of our bonds here, my yellow bonds, is actually 2 electrons. And so those electrons are going to be repelling each other. And when we're in this state here, we actually have those bonds fairly close together. So that creates a higher energy state or a less stable state. So this is a lower stability state or a higher energy state. We also refer to it as an eclipse state. So we say it's eclipsed because, of course, my hydrogen atoms are essentially eclipsing each other. Everything is right in front of each other, kind of overlapping with the stuff on the carbon behind it. So this state is eclipsed, and it's going to start out high energy. And I'll go ahead and draw out my representation with my Newman projection again. So I have my 3 hydrogens coming off the first carbon, going to the center of that circle, and then my 3 hydrogens coming out from behind the circle, representing the hydrogens on my back carbon. Now let's start to rotate it. And as we rotate it, we get to a point here where everything is staggered. Right? So what we mean by that is that none of our bonds are right in front of the other, and we've maximized the distance between the electrons of our bonds. So this is going to be more stable because we have more separation between those negative charges that repel each other. Our bonds are all staggered, right, where none of them are right in front of the other. And so this conformation state will be much lower energy. So we drop off to a minimum. So this occurred after I rotated it 1/3 of the way towards my full rotation of 180. So this is my 60-degree rotation. And I get to my low energy staggered conformation. I'm going to represent this with a Newman projection. So I have my circle representing my 2 bonds, and now I rotate it around so my front hydrogen points down, and my back hydrogens are still in the same relative orientation. So you can see how staggered they are, where each of my hydrogens are in a separate position. Now I can continue to rotate it, so that was only 60 degrees. I rotate another 60, and notice I'm again in the same eclipsed conformation. So my energy increased up to that same unstable point where my electrons are close together and they're repelling each other. So I have another eclipse state. My structure would look exactly the same here. Again, I show those hydrogens peeking out from behind on the back carbon, and I've reached 120 degrees. This conformation is exactly the same as my original eclipse conformation. You can see that in our energy states as well. We've gone from high energy to low energy in that staggered state, back to my high energy eclipse state. I can continue my rotation. Another 60 degrees gets me to 180. And again, you see I have the exact same staggered conformation. So my diagram will continue, and essentially a sine wave. We drop to our low energy staggered conformation at 180, back to our high energy eclipsed at 240, staggered at 300, and then of course at 360 we return to our original conformation. All of our high energy states up here are all equivalent eclipse conformations, and all of our staggered states down here are equivalent staggered conformations. 180, 240, 300, and of course at 360 we return to our original position. So we rotate, this was at 180 to our 240, 300, again staggered you can see, and 360 back to my original position in that eclipse conformation. So my ethane molecule can freely rotate, but not every position is going to be the same, right? So it's going to be rotating, but it's going to kind of want to slow down and stay at the staggered spots and kind of rotate more quickly through the eclipsed positions. So it will still be able to move freely and rotate between my different conformations, but there will be certain preferred conformations with those lower, more stable energies associated. Next, we want to consider the conformations of a more complicated alkane, such as my butane shown here. So we're again going to use my Newman projections. We're going to look down the bond between my two central carbons. So my carbon marked in red will be my front carbon, and then we're going to look at this back carbon rotating around. So we'll start out with 0 degrees, where my two methyl groups, the carbons at the ends, are both pointing up, and we create an eclipse conformation. However, whereas before we were just talking about the electrons in our bonds and wanting to maximize the distance between our bonds, here we also have these two methyl groups. And you'll notice these methyl groups are actually quite close together, so close that we can actually end up touching our hydrogens together. This will create a lot of steric repulsion between our atoms. So our atoms can't overlap, they push each other away. There's a lot of repulsion between atoms. They want to sit, of course, at a normal bond distance. If they get too close, we have repulsion between their electron clouds, as well as repulsion between the nuclei themselves that don't want to overlap. So, in this 0 degree angle, because we have our two methyl groups very close together, creating all that steric hindrance, all the crowding we call it, this is going to be a very high energy state. So we start out at a very high energy, much higher than our eclipse conformation in ethane. And when we draw out this conformation, we show, of course, our two carbons, our methyl groups, coming out the top, overlapping, and creating all of that crowding or steric hindrance. Again, I have my groups on the front, red carbon, and then of course the groups sticking out from behind, representing the groups on my back carbon. This black guy back here. This is still an eclipse conformation, it's just that it's a higher energy eclipse conformation compared to the eclipse conformation of my ethane. Now, as I rotate, I'm going to get to a staggered conformation, just as I did before. Again, you can see all my bonds are staggered, but I still have my two carbons at the end, the methyl groups, relatively close together. Right? So we're still going to see some steric hindrance between these two carbons. So this is going to rotate. We get to our staggered conformation at 60. We do decrease in energy significantly, but we're still relatively high in energy due to that steric hindrance. So we have our front carbon pointing out to the side somewhat. We've got our hydrogens. Our back carbon is still pointing straight up. So I've rotated my front carbon and created this new staggered conformation. Okay, let's rotate another 60 degrees. We rotate and we get to, again, an eclipse conformation. Now the interesting thing to note here is that unlike ethane, where all of our eclipse conformations were the same, this eclipse conformation is much better than the previous eclipse conformation. My two carbons at the ends, those methyl groups, are much further away from each other, and we're going to have less steric repulsion between these two carbon groups. So although we're still in a high energy eclipse conformation, so we go back up here, it's lower energy compared to my original eclipse conformation. So in terms of our Newman projection, we have our methyl group rotated down here on the front carbon. Overlapping with a hydrogen now instead of my carbon on the back carbon, my methyl group. And so even though it's eclipsed, it's a lower energy eclipsed state. Now we rotate again, and we've reached 180 degrees. At this point we're again staggered, all of our bonds are staggered relative to each other, but we've actually arrived at the maximum separation between our two carbons at the end, our two methyl groups. So we dip down to our lowest energy at 180. We're still staggered state, we're just a much better staggered state. So our carbon is all the way down at the bottom from the front carbon, but it's at the top from the back, and we've maximized that separation in order to make our molecule as uncrowded as possible, right? So we don't have any of our atoms running into each other and creating that repulsion, that steric hindrance. So we have two different staggered states and two different eclipse states. And we're actually going to use a couple new terms in order to refer to these different unique staggered states. So this one at 60 degrees, we're going to refer to as gauche. So gauche refers to our 60 degree staggered, where it's still staggered, so it's still a good conformation, but we still have our groups, our large groups, our carbon methyl groups, relatively close to each other. At the 180 degree angle, we've completed our half rotation. We're on the opposite side, and we refer to this as anti. So anti is the best conformation, the most stable conformation, because we've, again, staggered our bonds while also maximizing the distance between our two big methyl groups that are crowding each other. We don't have any fancy names here between our two eclipse states. Now we can continue our rotation, but the next rotations are all the same as our first. So here we have another eclipse conformation. This is the slightly lower energy eclipse conformation. So we go back up here, and you can see how symmetrical it is. We rotate again, and we get another gauche staggered conformation, but with our carbon on the other side. So we go on to our staggered conformation, but not as good as our anti. And then, of course, our final rotation brings us back to the worst eclipse conformation at 0 or 360 degrees. So we get this very symmetrical rotation with one anti-conformation that's the best. We have our worst eclipse conformation, and then our two gauche staggered conformations that are somewhat worse than the anti-conformation. So what this tells us is that our molecule will have a preferred orientation, right? It wants to sit in this anti-state. Now if we take a look at this, this is our anti-state, right? So we had our two carbons on opposite sides in the anti-staggered conformation. As I rotate this, you can see we get kind of this zigzag shape between our carbons. And this is actually where we get that zigzag line that we use in our skeletal structures, right? So you can see that zigzag represents the zigzag that our carbons want to sit in order to get that anti-staggered conformation. So most of our carbons, and then we can draw much larger alkane chains, of course, and they'll have somewhat more complicated conformational diagrams, but they're all going to follow the same key principles. They want to kind of get this zigzag staggered state where they can limit the crowding of our different carbon groups and also keep that maximum distance between our bonds in that staggered conformation. And again, this doesn't mean that you'll never see an eclipsed molecule. It just means that we're less likely to be eclipsed. So kind of if you grab 5 molecules from a set of 1,000,000 molecules, you're more likely to happen to grab molecules that are in the anti-state rather than eclipsed molecules. It's not that eclipsed molecules don't exist, it's just that they tend to rotate quickly through that eclipse state, and they want to kind of linger in that anti-state. As we'll see later, this will have some important implications for different reactions, because the shape of our molecule, the orientation, is actually going to affect how our molecule will react with other molecules.